All right, let's dive right into this explainer. Today, we're exploring the architectural blueprint of our skeletal system. Now, if you're an FSC first year or Cambridge A-level biology student, you are literally in the exact right place. We're going to break down all the high-yield facts you absolutely need to conquer those exams. And don't worry, we're skipping all that university-level overload.
But hey, before we get into the heavy histology, we actually need to totally change how you look at a skeleton. Seriously, bones are living, breathing, highly vascularized construction sites. They're not just some dead, dry scaffolding. I mean, from the moment you're born right up to this very second, your bones are constantly, and I mean constantly, being demolished and rebuilt. It's what keeps you moving, stores your vital minerals, and protects your internal organs.
So here's our roadmap for today. We're moving logically from the macroscopic anatomy straight down to the microscopic cellular level. We'll cover the skeletal framework, look at cartilage, the bone cells and matrix, compare compact versus spongy bone, touch on ossification, and finish up with a high-yield exam summary.
Section 1, the skeletal framework and morphological classifications. Let's start with the macro view. How do we actually classify bones based on their gross physical shape?
Well, there are 5 major shapes found in the human body, and honestly, form absolutely follows function here. First off, you've got long bones, like your femur. These are built to support weight. Then there are short bones, like the ones in your wrist, which are all about stability. Flat bones, think of your skull, act like literal protective shields. Sesamoid bones are pretty cool. They're embedded right inside tendons, like your kneecap, to protect against immense wear and tear. And finally, irregular bones, like your vertebrae, which have these super complex shapes to protect vital tissues like the spinal cord.
All right, Section 2, cartilage, the flexible foundation. Let's talk about hyaline, fibrocartilage, and elastic cartilage. Cartilage is basically the precursor and structural partner to bone. It's a specialized, firm connective tissue, but here's the kicker. It's avascular. That means no direct blood supply at all. It relies entirely on diffusion to get its nutrients.
Now, there's a really stark contrast between these types. Hyaline cartilage. It's the most common, but surprisingly enough, it's actually the weakest. It's got this clear, almost glassy look to it, and it acts as the original blueprint for our embryonic skeleton. But on the flip side, we have fibrocartilage. This one is the absolute strongest type. It's packed with these dense, alternating layers of collagen, making it a phenomenal shock absorber. That's exactly why you'll find it cushioning the intervertebral discs of your spine. Oh, and as a quick side note, elastic cartilage is full of flexible fibers, which give structure to things like your external ear.
Okay, stop whatever you're doing and take notes right here, because this is a massive exam trap. You absolutely have to know the difference between these two growth mechanisms. Interstitial growth happens from the inside out. Chondrocytes divide and secrete new matrix from within the tissue, kind of expanding it like a balloon. Appositional growth, on the other hand, happens on the outside. Stem cells in the surrounding perichondrium turn into chondroblasts and literally add fresh layers of matrix right onto the surface of the existing cartilage. So within versus surface, make sure you lock that distinction in your memory for sure.
Moving on to Section 3, bone cells and matrix. Time to check out the cellular construction site and meet the microscopic crew responsible for building, maintaining, and remodeling our skeleton.
So the really crucial point here is being able to identify 4 distinct cell types and, really understanding their specific jobs, because they all work together in this highly coordinated biological dance.
To easily remember this for your exams, try anchoring these scientific terms to everyday construction roles. It really helps. Think of osteoblasts as your active construction workers. They're the ones secreting fresh bone matrix and laying down collagen. Then you have osteoclasts, which are basically the demolition crew. These are big, multinucleated cells that secrete enzymes to break down and resorb old bone tissue so it can be built back even stronger. Next up, osteocytes. Think of them as the retired managers. These used to be osteoblasts, but they got trapped inside the very bone matrix they built. Now they just sit in little caves called lacuna and manage the surrounding tissue. And finally, osteogenic cells. These are your trainees, just stem cells waiting to differentiate into osteoblasts when duty calls. Honestly, just remember this mnemonic. Blasts build, clasts crash, and sites sit.
But what exactly are those osteoblasts building, right? Well, they're laying down the bone matrix, and this stuff is a practically perfect composite material. About 2/3 of it, roughly 66%, is made of really hard inorganic salts, specifically calcium hydroxyapatite.
This is what gives your bones that incredible hardness to resist compression. The remaining 1/3, or 34%, is the organic matrix, which is mostly collagen fibers. And this organic part is absolutely critical because it provides tensile strength and flexibility. Without it, your bones would literally shatter like glass under pressure.
All right, section 4, compact versus spongy bone. Now that we know what bone is actually made of, let's look at density and distribution to compare the two main architectural styles of mature bone.
It's super cool how these two styles beautifully complement each other. Compact, or cortical bone, makes up a whopping 80% of your skeleton. It's that dense, hard outer shell providing all the structural support and protection. Spongy, or cancellous bone, makes up the other 20%. You'll find this on the inside, especially at the ends of your long bones. It literally looks like a porous honeycomb made of tiny bony plates called trabeculae. It's a really brilliant design because it keeps the skeleton lightweight enough for you to actually move, while safely housing the blood-producing red marrow right inside those honeycomb spaces.
When we zoom in and look closely at a transverse view of that compact bone, we see it forms this microscopic Haversian system, also known as the osteon. This is the fundamental functional unit of all compact bone.
Think of an osteon, kind of like a microscopic tree trunk running the entire length of the bone. Right in the very center, you've got the Haversian canal. Think of this as the central plumbing and highway system. It carries vital blood vessels and nerves. Surrounding that canal are these concentric rings of hard bony matrix called lamella. Literally, just like the rings of a tree. Trapped between those rings are retired managers, the osteocytes, sitting in their little caves called lacunae. Now, because this matrix is rock hard, these trapped cells need a way to get nutrients. Enter the canaliculi. They are these tiny microscopic communication channels radiating outward, letting the cells share nutrients. Finally, you've got Volkmann's canals running perpendicularly, linking the vertical systems together. Honestly, it's an absolute marvel of natural engineering.
Section 5, ossification, building the bone. So how does all this incredibly intricate tissue actually form during human development? Let's check out the intramembranous and endochondral pathways.
And right out of the gate here, we have another major exam trap. You really have to know the difference between these two pathways. Intramembranous ossification is basically the direct laying down of bone right into primitive connective tissue. This is exactly how flat bones, like your skull, get formed. But endochondral ossification is totally different. It strictly requires a pre-existing hyaline cartilage model to act as a template before any bone can actually be built.
For long bones, the ones in your arms and legs, this 4-step endochondral process is essential. First, a tiny hyaline cartilage model of the bone develops in the embryo. Step 2, the cartilage cells grow really large, they hypertrophy, and the surrounding matrix begins to calcify and harden. This actually shuts off their own nutrient supply. So step 3, because that tissue is dying, blood vessels invade the area, and they bring along our construction workers, the osteoblasts. Finally, in step 4, those osteoblasts get right to work. They deposit real bone matrix over the calcified cartilage remnants and hollow out the center to form a primary marrow cavity. It's this beautiful, meticulous replacement of a temporary template with hard, vascularized bone tissue.
Section 6, our high-yield exam summary. We have covered a massive amount of cellular histology, gross anatomy, and developmental biology today, so let's distill all of this down into your ultimate 10-second takeaways. Okay, if you're going to take a screenshot of anything today, this is the moment. Memorizing these specific points is going to secure you those high marks. Remember the matrix ratio. 2/3 inorganic for hardness, 1/3 organic collagen for flexibility. Keep those construction cell analogies in mind. Blasts build, clasts crash, sites sit. Never forget that cartilage is avascular. Strictly separate interstitial growth from appositional growth. And always remember that osteons belong entirely, exclusively to compact bone.
To wrap things up, I want to leave you with this pretty provocative thought to test your understanding of remodeling. We know bones constantly adapt to physical stress, right? So what happens to the skeleton of an astronaut floating up in the zero gravity of the International Space Station? Well, without that constant downward stress of gravity, the demolition crew, the osteoclasts, actually start to dramatically outpace the construction workers. Crazy enough, astronauts can rapidly lose bone density in space. It just goes to show how brilliantly, and honestly sometimes dangerously, responsive our skeletal system really is. Anyway, thank you so much for joining me for this explainer. Keep reviewing those notes and best of luck with your studies.